In this video, we are going to look at understanding Snell's law and refraction from a conceptual point of view. So let's recap the last video. I didn't maybe mention this explicitly as much, but we did see that light bent toward the normal when it entered a more optically dense material. And so the angle of refraction was smaller than the angle of incidence in that case. It bent toward the normal. In the other direction, light will bend away from the normal when it enters a less optically dense material, when it enters a material with a smaller index of refraction. Why does this happen? So let's go ahead and look at this from the point of view of the toy car model of refraction. It's a great video. I'm just going to let it speak for itself. I do want to point out that the analogy here is we have a fast material here for toy cars. Then we got this like shag carpety type stuff, so it's a slow material for cars. And then we go back to the same fast material for cars. All right, let's watch this together. All right, so in that we could see that when the lights, there it is. When the car goes into the carpet, the right wheel catches before the left wheel and it makes a turn toward the normal. And then when it leaves, the right wheel sticks around longer and it makes that turn back in the same direction as propagating before. Light behaves similarly. This video is of the same idea. It comes from a great physics teacher by the name of Joe Cassette. He gets credit. If I remember, I'll link both the last video and this in the description of the YouTube video. Let's watch this together also. So how can we predict which direction the light will bend? Bends toward the most optically dense medium. Bends toward the normal, that is. All right, there we go, folks. If you need to rewatch that, I encourage you to do so. But there's that same sort of toy car idea. We're going to bend away from the normal as we go into the faster material. We're going to bend toward the normal as we go into the slower material. Refraction can also be explained by the fact that wave speed and wavelength decrease when entering a new medium. So we can also use the wave model to explain the idea of refraction. Got a great animation here to show about that concept. Let's copy that URL. It wasn't letting me click for some reason. All right, here we go. Light's coming in, and it enters that boundary at an angle. At the other end, we have a shorter wavelength because we have slowed down and the waves bunch up. And the only way to match up is with some refraction. Let's watch that one again. Light's coming in at an angle relative to the boundary. In order for the boundary to match up at both ends, we need to rotate the blue wave because its waves are more scrunched together. So this boundary matching gives us refraction. I'll link this in the description of the video too. All right, folks, that is the end of our PowerPoint here. I hope I gave you a few ways to think about the concept of refraction using the toy car model and the boundary matching for light waves.